Good afternoon, everybody. Welcome back to the Math 140 Healthcare Series. And we're going to look at sets and Venn diagrams today and start our adventure into Unit 3, which is Introduction to Probability and an Introduction to Conditional Probability as well. All right. So, now, even you may wonder why we're dealing with sets if we're doing a chapter basically on probability. So it turns out that sets are a basis, well, pretty much of all mathematics, but they're very important structures to understand in order to do probability or statistics. So that's why we start there. And I try and keep it to the relevant information and the stuff that we need to know about them in order to do the work we want to do. All right, and just a reminder, if you're watching this video, hit pause if you want to think about something. Email me if you have questions. All right? All right, so we often deal with collections of different kinds of objects. For example, if we were studying student performance, all right, in math courses, we might consider the collection of all students taking Math 140, all right? Or if we're studying college parking, we might consider the collection of all parking spaces at FECC. Those are collections of objects. And that is all a set is a well-defined collection of objects. Well, what do I mean by well-defined? Well, you can't talk about the set of days last year where it was a pleasant temperature. We don't know what that means. Is 75 a pleasant? Is 85 pleasant? Is 65 pleasant? Whereas we can make that a well-defined set and say the set of days from 2020 where the high temperature of the day was between 65 and 85 degrees, something like that, then it's well defined. And that's all we mean by well defined. You have to be able to tell, is it in there or not in there? Can't be a on the fence question. And that's what we're saying here. The phrase well defined means we are given an object. We must be able to determine whether or not it belongs to the collection. For example, the collection of good students in Math 140 is not a set, since it is not clear what we mean by good. Think about how you could make that a well-defined set. All right. Now, the objects of sets are called elements, or members of the set. The elements are usually denoted by lowercase letters A, B, C. The sets themselves are usually denoted by uppercase letters, capital A, capital B, capital C, and so on. The elements of a set can be displayed by listing all the elements between braces or curly brackets, however you want to say that. For instance, here I'm defining my set A to be the set of the elements A, B, C. And I want to make a note here is order does not matter. It's a collection of objects, not a sequence of them. So this is equal to the set B, A, C. It doesn't matter which order we're in. And that is partially, I want to note why the curly brackets are necessary. Whereas if you recall, say a point in the plane, maybe 1, 2, that's an ordered. When we have parentheses, we usually mean ordered. Okay, so this is not equal to 2, 1, right? They're not the same point in the plane. So just to note, that's why those curly brackets are there and why they're important. They do have meaning to them. Okay? Now, we could also write set B with the 3 dot notation when it's clear. For instance, here B equals set 1, 2, 3, and it's supposed to be 4, 5, all the way up to 20. Hopefully we read that. All right. Another way, and that's called roster notation. Sometimes it's inconvenient to list every element, and we could use set builder notation. For example, our set B can be listed as this. This is read as B is the set of elements X such that X is a positive integer less than or equal to 20. All right, and hopefully we see how that gives us the set B that we saw in roster notation. Take a minute, take a look at these two. Which one of these are a well-defined set? You hit pause and think about it. Yeah, B is well-defined, but not A is not. Right? A, approximately. What do we mean by approximately? We have to be clear about that. We could think that 71 is approximately 73. I would say 71 is approximately 73. But we want, in B, we set exact what it has to be. To be approximately 73 degrees, it means to be between 72.2 degrees Fahrenheit and 73.3 degrees Fahrenheit. And I will say is defining your sets is going to be a lot like defining your variables in Unit 1. If little a is an element of the set capital A, we write A is in A in capital A, or A is an element of the set A. That's what we mean by this symbol here. And by the way, that symbol, it looks kind of like an E. It really means exists in. Right? A exists in big A. But we can read it as A and is an element of set A. If A does not belong to the set, just like not equal to, we just put the slash line through it, and we read A is not an element of the set A. Now, two sets are equal if and only if they have exactly the same elements. Exactly the same elements, okay? Doesn't matter the order, but exactly the same elements. And that's what we're saying here. Notice the order doesn't matter. The set containing 1, 2, 3 equals the set containing 2, 3, 1. They have precisely the same elements, so they are equal. Doesn't matter the order, but precisely the same elements. The idea of subset is also quite important, and we will see this, I promise you, when we get to the probability section, how important these subsets are. But here, if every element of A is also an element of B, then we say that A is a subset of B, and write A, and a subset of B, that's how you would say it. And notice that subset sign, it should remind you, it's kind of like the less than or equal to sign, okay? Pretty much, it's the set equivalent of that. All right, now let's see. If we have these three sets, can we tell which are subsets of others? Okay. Well, C is clearly not a subset of A or B because it has too many elements. But let's see, A has 1, 2, 3. 1, 2, 3, 4 is also in C. 1, 2, 3, 4. So that means that A is a subset of C, since every element of A is in an element of C. And A is not a subset of B, since we notice that 1 is in A, but 1 is not an element of B. Likewise, B is not a subset of A, since 8 is in B, but 8 is not in A. Couple things to notice about subsets. For all sets A is always going to be a subset of itself, okay? And since every element of A is an element of A, that's certainly going to be true. If A is a subset of B, but we know it's not equal to, then we say A is a proper subset of B. Okay, and write this without the equal sign, where this is kind of like the strictly less than sign. proper subsets are much less important than the idea of subsets. The empty set is an important set. In the world of sets, it kind of acts like the number zero. And the set that contains no elements is called the empty set and is denoted. So if you make your zeros like this, you really need to stop and use this for the empty set. What the empty set looks like is the set that contains no elements, which I want to be clear is not the same as the set that contains 0 as an element. Okay? That's important. Empty set has no elements in it. It's kind of a weird thing, but we're going to see how it's quite useful. For all sets A, like we saw, A is a subset of A, and also the empty set is a subset of A. Right? Since it's empty, no matter what set A is, the empty set is a subset of it. Okay. Oh, and another, not only the set, notice that the set containing the empty set is not the same as the empty set. Also note that if A equals 1, 2, 3, we have that 1, 2 is a subset of A, proper subset. Sorry, the set containing 1, 2 is a proper subset of A. The set containing 1 is a subset of A, but we don't write the set 1 is an element of A. We write 1 without the braces as an element of A. Subsets of A here are as follows. The empty set, 1, 2, the set containing 1, the set containing 2, the set containing 3, so on and so forth here, all the way up to A itself, the set containing 1, 2, 3. So notice A has 3 elements in it, and the number of subsets of A is 2 to the third. In general, if a set has k distinct elements, then there's 2 to the k subsets of that set. Now, if you want to think about why that's true, it has to do with each element could either be in there or not in there. You could try and make a tree diagram to think about it. There's a few ways, but we will in the next module learn more counting where it becomes, we'll see this as clear. Which of the following sets is not a subset of A equal to the set containing 0, 2, 4, 6, 8? Okay, well, we know A is a subset. We know the empty set is a subset. See 2, 4, 6, they all appear in A, so that's a subset. 2, 5, 8, that is not a subset, right? There's no 5 up in here. Even though 2 and 4 are both in A, 5 is not. How about this one? X, such that X equals 2n, where n is an integer between 0 and 2. Why don't you take a minute? What is that set? You maybe hit pause and see if you can figure out what that set is. Between 0 and 2. So 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. So it's the set 0, 2, 4. And that is a subset of A. So 2, 4, 5 is the only one that's not a subset. Alright. In contrast with the empty set, we have the notion of a largest or universal set. And a universal set is a set of all elements of interest in a particular discussion. Of course, different universal sets are associated with different problems. If we want to determine the ratio of male to female students at the college, we would take our universal set to be all the students at the college, okay? All the students at the college. That's our universal set. That's what we're interested in. However, if we want to determine the ratio of male to female students in Math 115, we would take our universal set to be all the students taking Math 115. Okay? So that universal set has a lot to do with whatever problem we're working on. There's no general universal set that's universal. Okay. Now, one useful visual representation of sets is called Venn diagrams. The universal set, or the universe, is denoted by a square. And if we have two sets, say A and B, we simply, those each are represented by a circle. Okay? And I'm gonna, where this is A and this is B. And notice, so what do I mean here? The green shaded region is all the elements in A. The red shaded region is all the elements in B. And the region that's both red and green, well, just like it means that there are elements that are in both A and B. So I'm going to stop this video here, and we'll continue with Venn diagrams in the next video.